Good day, class. So we will continue with techniques of integration. So we're done with the first two portions of these techniques of integration, wherein we have discussed the exponential function, the logarithmic function, the trigonometric functions that are complicated, that needs us to transform it into more, shall we say, manageable trigonometric expressions, wherein the basic integral formulas could be applied to. Then we also are done with the integration by parts, and we're also done with, I think, the inverse trigonometric functions. So now, for this particular slide, we'll be talking about the hyperbolic function and the inverse hyperbolic functions. Okay. Now let's start this slide with a review. So you could see in this particular slide that on the left column, you have the derivatives of the 6 hyperbolic function. We have the sine, the cosine, the tangent, the cotangent, the secant, and the cosecant. So these are the derivatives. Now, if these derivatives of these functions are integrated, now it would be yielding back the original function which we have differentiated here. So these are, shall we say, the standard integration formulas for hyperbolic function. So hyperbolic sine and cosine now will have all integrals being positive. The hyperbolic secant squared will be positive hyperbolic tangent. The hyperbolic cosecant squared will be negative hyperbolic cotangent of u. And the hyperbolic secant hyperbolic tangent of u will be integrated, yielding a negative hyperbolic secant. The same thing with the hyperbolic cosecant hyperbolic cotangent product. If integrated, will yield also a negative integral, which is the hyperbolic cosecant of u. So this will be our basis in processing or evaluating the following integrals, which we'll be discussing in this set of slides. So we'll be using this standard integration formula for hyperbolic functions. Now you could see here in this slide that you're given the integral of the hyperbolic cosine of the square root of x dx divided by square root of x. If we will set the hyperbolic cosine of the square root of x to be the function that will be integrated, the u of this particular function is the square root of x. Now, it is a requirement in integral calculus that the du of whatever u that may be for a particular function should be present in the given integral as well. If it's not present, we just multiply it or divide it with the corresponding constant that is needed. That way, it will be complete. So if there's no way that we can process the said integral because it's really incomplete in terms of the derivative of the u of the given function, then that particular integral cannot be really evaluated. So I will go back to again saying that in this particular integral, you will be processing the integral of the hyperbolic cosine. And the u for such a function is square root of x, and there's a need for us to differentiate it, which will yield 1/2 square root of x dx. So in here, in this expression, the dx over the square root of x is already this particular derivative, only that you lack the 1/2. So what is done here is we integrate our original expression by multiplying it by 2 over 2. We need the 1/2 in the denominator here. That way our derivative will be complete and the 2 will be placed outside. Now your main function then is ready to be integrated, and that main function is the hyperbolic cosine, which we know is just the hyperbolic sine. This being equivalent to the hyperbolic sine function multiplied to the 2, which is written before the integral. So that would yield an expression which is the hyperbolic sine of the square root of x times 2 plus c. Okay. Now, in this particular example, we have placed a combination of an exponential function and a hyperbolic function. But we would like to see, or we will try that our main function to be integrated in this case will be the hyperbolic squared of secant e raised to x. If that is the case, your u is e raised to x, meaning the hyperbolic secant squared will be your main function. So the du of this expression is actually your e raised to x dx, which is the one that you are seeing here. So this e raised to x dx is the du that is written in here. Now then, we are ready to integrate the hyperbolic secant squared of e raised to x, which is actually, as what we have discussed based on the formula set in the other side, in the other slide, will be the hyperbolic tangent of e raised to x. Okay? Now, we can also have this expression. So the hyperbolic sine divided by 1 plus hyperbolic sine squared x. Now, this 1 plus hyperbolic sine squared x has an equivalent expression of hyperbolic cosine squared of x. Okay? This is equivalent to this. Now, this can be split into two hyperbolic cosine function, and this one will be set as tangent, hyperbolic tangent of x times hyperbolic secant of x, which will represent an integral that is already basic, in which we can apply the formula of. So we have this one, the hyperbolic tangent of x here, and the hyperbolic secant of x here, which will yield an integral which is the negative of the hyperbolic secant of x. So all we need to go back to are the basic formulas for integrating hyperbolic functions. Now let me clear the marking. So in here, again, we have a mix of the exponential function and the hyperbolic cosecant squared of x. Now, if we set this particular function as the main function, the hyperbolic cosecant squared of x, the remaining expression cannot be the derivative of this expression, because this particular function in itself is standalone. It can be evaluated already in terms of an integral. So in this case, we cannot set the hyperbolic cosecant squared of x as the main function to be integrated. So that's a trial and error thing. Now, since this cannot be integrated, we will check whether this exponential function could be. So if the e raised to the hyperbolic cotangent of x will be our main function, then it is a requirement that we should have the derivative of this hyperbolic cotangent of x, which we know is the negative of the cosecant, hyperbolic cosecant squared of x. So it's written here already. So the only thing that's missing here for the derivative of the argument of your exponential function is the negative sign. So we can address that easily by writing a negative sign in here and writing a negative sign outside your given integral. So if it's done in this manner here, you could see that you have already EU as your main function, and this is the DU. It's already complete. And we know that EU du has an integral which is equal to e raised to u. So let's check whether it's really e raised to u. So e raised to u, which is the hyperbolic cotangent of x, and we just affix the negative sign that was written before the integral. So in this case, class, in example 4, you're not integrating a hyperbolic function, but rather you are integrating an exponential function which has an argument which is hyperbolic in nature. So actually, it's not the integral of a hyperbolic function, but an exponential function. Now let's go to this example, the hyperbolic cosine squared of x. So just like the square of a cosine, now the hyperbolic cosine squared of x has a double, so say double angle in analogy equivalent. So it's also plus here, and it's 1 here, and you have 2. So 1 plus hyperbolic 2x, hyperbolic cosine of 2x over 2 is the equivalent of hyperbolic cosine squared of x. Now with this, it's so easy what's to be the next step. So you have to expand the given integral and evaluate each of the terms separately. So that would mean you will have 1/2 integral of dx for the first term, and 1/2, another 1/2 integral of the hyperbolic cosine 2x for the second term. This will have an integral which is 1/2 x, and the hyperbolic cosine will have a hyperbolic sign as long as the derivative of the 2x here is complete. In this case, you don't have a 2. It should be a 2 dx. So you introduce the 2 here and you write another 1/2 before the integral. That's the reason why you have here 1/2 times 1/2. This one is for this one is for this particular constant, and this 1/2 is for the other 1/2 that will be actually multiplied to the 2 that you introduced here for the derivative of the 2x in the argument of your hyperbolic cosine. So in that sense, this is now our integral. 1/2 x plus 1/4 hyperbolic sine of 2x. Okay? Now let me erase my markings here again. Okay, now we proceed. Now, we're done with hyperbolic functions. Then we'll be now ready, or you're now ready to, let's say, process integrals which will yield the inverse of a hyperbolic function. Now, this is similar to the inverse of trigonometric functions. Okay? Now, the difference of the hyperbolic function with the trigonometric function is in some way the signs that separate the a squared and the u squared, or the 1 plus the u squared, and the radical sign that is present in the denominator of some of the expressions, whereas in the other, there isn't any radical sign or square root sign. Now, as a review, in your differential calculus, we know that these are the derivatives of the following inverse hyperbolic functions. So inverse hyperbolic sine will be this one. Same thing with hyperbolic cosine, the inverse of that, up to the inverse of the hyperbolic cosecant. These are their derivatives. So based on the concept of the derivatives, the antiderivative of that, which requires you to integrate the derivative, will give you back the original function which was differentiated. So the integral of du over u squared plus 1 is the inverse hyperbolic sine of u. So your difference with the hyperbolic sign, or the difference of the hyperbolic sign with the hyperbolic cosine, is the sign that separates the u squared from 1. So if it's hyperbolic sign, it's plus. If it's hyperbolic sign, it's cosine, it's minus. The hyperbolic tangent, and take note of this, and the hyperbolic cotangent will have the same denominator. So it's a 1 minus u squared. The inverse hyperbolic secant and the inverse hyperbolic cosecant, if you're going to look at it in the same way with the sine and the cosine, the inverse hyperbolic sine and the inverse hyperbolic cosine only differs in the sign that separates the 1 and the u squared. It's inverse hyperbolic secant if it's a minus sign, and it's inverse hyperbolic cosecant if it's a plus sign that separates 1 from the u squared. And by the way, class, it's important that you're going to understand that this u could be any algebraic expression like x squared, x to the 4th, x cubed, x to the 6th, x to the 9th. It could also be a function, okay? Now, in here, you have u for the hyperbolic or the inverse hyperbolic secant integral, and in here you have the absolute value of the u for the integral yielding the inverse hyperbolic cosecant. Okay, So let's look onto some examples where we can apply this inverse hyperbolic function integral. Now, there are also equivalents, by the way, so this would be expected of the integrals of this particular expression. Just like the inverse trigonometric function, you may wonder why, what if the numbers that you're seeing here is not 1? What if it's any number like 3, 7, 9, 4? This one, if it's not 1, there must be some alternative that could be used. And that alternative is presented here. So if you have the integral of dx over the square root of a squared function plus minus any constant. So a squared here could be any constant. It could even be not a perfect square constant, but it's a constant. Then that would yield an ln. The ln of du plus the square root of u squared plus minus a squared. So if you have a plus here, this is plus. If you have a minus, this is a minus. Okay? Now, this is second, right? The inverse hyperbolic second. The thing is, in hyperbolic second, this should be 1. In here, it could be any constant. So since you have replaced the 1 by another constant, your integral this time will yield not an inverse hyperbolic function, but an ln function, just like what we have here on top. So your a must be identified. It could be any real number that can have a square root. Then your u should also be well identified. Now remember that this u could be algebraic, or it could be also any function like exponential, trigonometric, ln, as long as you have the derivative of that particular u in here, there's no problem. It would still yield this particular answer. Okay? Now, if you have a case of 1 over a constant minus u squared, it would not have been a problem if this is plus, because it will just yield the tangent. Okay? If you recall the tangent function, if you have 1 plus u squared, or that would be the inverse tangent function. Now, in here, it's minus. So it is now yielding this particular integral. Identify the a and identify what is the u in this u squared expression. Make sure that its du is complete here. Then you can write this particular answer for this integral. So take note, this is not 1, because if this had been 1, this would be inverse hyperbolic tangent. But since it's not 1, then it's a function of, or rather it's called as the logarithmic function. The natural logarithmic function is your integral for such an expression. There's a correction in the study guide that some of you probably have already read, so there's no 2 in here. So it should only be 1 over a, the ln of a plus u, all over a minus u. Okay? Now, this one is for cases wherein your a is not 1. So you have the ln, or this could also be yielding the inverse hyperbolic sine u over a plus c. If, take note, if the sign that separates these two is positive. Meaning, class, you have 2 possible answers for an integral of the square root or the integral of dx over the square root of a function that is squared plus a constant. You can have this, or you can have the hyperbolic, the inverse hyperbolic sign. If it's a minus, it's u squared minus a constant, then your answer could be this, minus here, or it could be the inverse hyperbolic cosine of u over a plus c. So take note that you have 2 possible answers in this particular scenario. Actually, even 3. Okay, because if this a is equal to 1, you will have an outright answer of this one. This one. Okay, If it's 1, it's either inverse hyperbolic sine or inverse hyperbolic cosine. Okay? Now, so that would be for this one. But in here, in the case of a comparable integral expression for the inverse hyperbolic secant, when the 1 is not 1, but rather any constant, it should be having this answer as the, or it should be having an answer which is in the form of a logarithmic function. Now let's go to specific examples. So you have 1 over 25 minus x squared. Looking closely, you see that 25 is a perfect square and x is also a perfect square. So if we set u as x, the du of that is dx. So we don't have any problem. It's already in here. Our a is 5. And since we don't have a 1 minus x squared, then this will be yielding a ln, an ln expression that was presented to you a while ago. So the ln formula in here, so let me go back to that in here. This one last part, okay? If this would have been 1, that would be an inverse hyperbolic tangent. But since this constant is not 1, then it would be yielding a logarithmic function, a natural logarithmic function. So you just follow the formula, and this is our answer. Just correctly place in the a and the u, which you have seen in your given integral. Now for number 2, this is comparable to the inverse hyperbolic secant. Okay? Inverse hyperbolic secant. So you have 1 plus 4x squared, meaning your u is 2x, the derivative is 2 dx. Your a is 1. Okay, so in that case, we will have to multiply. We need to multiply our regional integral by 2. That way, in here you see that this should be a u. In the inverse hyperbolic secant, so this should be a u. In your case, it's 2x, so you lock the 2 here. So you need to multiply by 2 over 2 so that you can make use of this one in here and the other one outside. So this is the one outside and this one is the one that's written here. Now, this original integral was already transformed into this form, which is readily integrable, meaning it's already complete. And you can apply the formula that is appropriate. Now, you can see that you have here your a as 1 and your u is 2x. So your answer will be 2 integral of, so it's like, by the way, this integral is comparable to this now. Or rather, this one, the more complete one, is comparable to this. So whenever you have this one, it will yield an ln. Okay? An ln. So 1, your a being equal to 1. Now, aside from this, you could see it's 1 plus a u squared. You can also have another answer. So if we go back here to the formulas that we have here, it could also yield the integral, which is the negative of the inverse hyperbolic cosecant. Okay, because it's plus. If it's minus, it's the negative of the inverse of hyperbolic secant. So it has to be, however, specified here that what you have written here is the absolute value of u. Now, if this particular u that we have in this example, let me go back to that example, is not at all times to be assumed to be absolute, then it's safe to answer a natural logarithmic function as the integral of this given expression, because the u is not specified to be absolute. But in this case now, since it's not specified, then it should be. If it's specified, you can write inverse or the negative of the inverse of hyperbolic cosecant of u. Okay? But there's nothing wrong with answering in terms of the natural logarithmic function. Okay? Now, I suggest that you process also integrals expected to be yielding hyperbolic and inverse hyperbolic function to complement what was discussed in this slide. So thank you for listening, class. I will be again recording for another topic that you could listen to. Bye for now.